Let me introduce myself. So I'm Rubén Seoane. I'm working currently as a postdoctoral researcher at Leijnse University under the supervision of Martin Leijnse. And today I want to talk about our recent work entitled Josephson diode effect in supercurrent interferometer. The idea of our work is to develop a new kind of Josephson diode based on Josephson or nanoscopic Josephson junctions in interferometers. And the main advantage is the tunability of these Josephson junctions, and actually that we don't need very unconventional superconductors to reach the Josephson diode effect. This is a work done in collaboration with Martin Leijnse and Constantin Schrade. Now, let me start with a very brief introduction about the diode effect, which I'm pretty sure that everyone in the room is actually familiar with. So the idea is to have an element that actually conducts in one direction, but becomes highly resistive in the other one. And this special characteristic made this element a core electronic element for applications, including rectifiers and well, many other applications I'm not going to mention today. But the important thing is that still in the conductive regime, there is still some finite resistance by the diode, and that has a drawback in some applications. So this is why it became in the last years very, so the question of finding a diode that only superconducts or shows zero resistance in one direction became really important in the last couple of years. And application of the devices range from a superconducting neural network, lossless amplifier, or supercurrent amplifiers, just to mention a few of them. However, there is a problem with designing this kind of elements. And the problem is that, or the issue is that if we have both time reversal or inversion symmetry, actually the supercurrent becomes symmetric with respect to the origin, where this is the current function, the supercurrent function of the phase. And that means that the supercurrent in the positive and the negative direction should be dissimilar, which means there is actually no diode effect because the critical current in both directions is actually similar. There has been a very fast development in the last couple of years or three, developing new kind of Josephson diodes. Starting from or including complex superlattices, twisted biologography in junctions, two-dimensional Josephson junctions, and many more that are not included here, and also several theoretical proposals that I haven't included here. But we will hear more about them in the next couple of days in this very exciting workshop. In this presentation, I'm interested on generating a Josephson diode that requires no Zeeman field and not a spin-off decoupling. So it's based on conventional superconductors. And this goal is to broaden the class of suitable materials to develop Josephson junctions. And also we are interested on setting up which are the minimal ingredients to get a Josephson diode and how to optimize the Josephson diode to the most efficient point. This is the outlook of the talk, where I will start with a very simple mathematical example. Then I will go to more realistic examples like quantum point contacts and quantum dots. And then I will talk briefly about a DL diode and actually how to optimize diodes and the signatures of this Josephson diode. But let me start with the basics. Let me start with a very minimal mathematical example. Well, as I told you before, if we have a junction with, for example, inversion symmetry or time reversal symmetry, the supercurrent becomes, the supercurrent in the positive and the negative direction becomes actually the same, meaning that the critical currents in both directions are similar, so there is no diode effect. Is there something we can do with actually a second junction? Well, in this example, I'm considering a second junction which has a very exotic current phase relation that actually has a double period with respect to the original one. And by the moment, this is only mathematical examples, and I will come later on physical realizations of this interferometer. So the idea is that when we make these two current phase relation interfere, there is actually not much happening, unfortunately. because still the current in the positive direction and in the negative direction is exactly the same. So we need to do something else to generate the diode. And the something else is to thread a flux through the superconducting loop. So this flux, what it does is to actually shift the current phase relation one with respect to the other. And in this way, we can make the maximum of the black curve interfere constructively with the maximum of the blue curve and destructively for the negative part. That means that the supercurrent in the positive direction will be higher than the critical current in the negative one, leading to a superconducting diode effect. Now, this is a nice, simple mathematical example, but is there a way? So, what can we learn from the from this example? So, the requirements for this Josephson diode is first we need higher harmonics, meaning that one of the two junctions should contain sine 2 phi or higher order harmonic in the current phase relation, or at least different from the original one. The second one is that the two junctions should contain different harmonic content, meaning that if I write the same CPR for the first and the second junction, they cannot interfere in different ways for the positive and the negative direction. And the third one is that there should be a finite magnetic flux, which should not be equal to half flux quantum or an integer value of half flux quantum. And that's basically to align the maximum together while the minimum aligns with the maximum and leading to this constructive destructive interference in both directions. Now, this is a very simple example, but is there a way to actually make such a Josephson diode? And the first example we have chosen is quantum point contacts. So these quantum point contacts appear in weak links between two superconductors where there is weak link between them. So there's one channel or a few channels connecting the two superconductors. And they have been realized in a number of systems, including mechanical brake junctions and nanowires. For the sake of this presentation, I will focus on the single channel situation. However, the conclusion don't change if we add more channels. Well, the current phase relation is very well known for these Josephson elements, and it is controlled by the parameter tau, which is called the transmission. As a function of the phase, we see it has a sinusoidal part, and then it has some dependence on epsilon L, which is the energy of the Andreev bound state that locate at the interface between the two superconductors. And these Andreev bound states, what they do is that they induce a non-sinusoidal CPR, or non-sinusoidal current phase relation when the transmission is high. So this is illustrated on the right, where the current phase relation for a low transmitting becomes sinusoidal, meaning that the maximum and the minimum of the current phase relation become evenly spaced. However, when we increase the transmission, the current phase relation becomes skewed, and the maximum and the minimum of this supercurrent are located very similar. So we can use the different location of the maximum and the minimum of the supercurrent to actually induce this constructive destructive interference in the different directions. And this is what is represented here. So we have a very high transmitting quantum point contact with this skewed current phase relation. And then we have a more lower transmitting quantum point contact with a sinusoidal or mostly sinusoidal current phase relation. When we sum both of them, we see there is a higher supercurrent in the positive direction with respect to the negative one, giving rise to a diode effect. And this is better illustrated in this plot where we represent the critical current in the vertical direction as a function of the magnetic flux through the loop. As you see, there is generally an asymmetry between the supercurrent in the negative direction in blue with respect to the supercurrent in the positive direction in red, except for some fine-tuned points, which is zero flux or half flux quantum. Now, I would like to mention that the current asymmetry between these two curves is relatively large, and it should be measurable using available technology nowadays. Now, we can learn a bit more from the diode efficiency. So the diode efficiency is just the difference between the red and the blue curve divided by the sum of them. And this is the conventional definition for the efficiency. And efficiency is represented in this color map, where the vertical axis is the transmission of one of the junctions, where we have fixed tau 1 to 0.7. So that's the horizontal dash line. And the horizontal axis is still the flux through the loop. Now, as you see, there is a sizable diode effect, which is around 40%, and that means that actually the supercurrent in the positive direction is around 2 times larger than the one in the negative one. What we can learn from this figure is that there are certain requirements for the Josephson diode to appear. The first one is the tunability of the flux that we have mentioned before. So the flux cannot be 0, but it also cannot be half flux quantum, because the places there is no diode effect. And the other one is the one denoted by the horizontal white line, where actually transmission of both junctions become equal, meaning that the current phase relation of both of the junctions have the same harmonic content. And in that case, it's not possible to make an asymmetric interference between the positive and the negative direction. So just to sum up, the requirements for a Josephson diode effect to appear in the system is we need high harmonics. So we need at least one of the junctions to be transparent or to have a relatively high transmission. And by relatively high, I mean that something above or of the order of 0.5, which is not challenging, I would say, given the current technology. Now, they should have a different harmonic content, meaning that they should have different transmissions. And also the magnetic flux cannot be tuned to and to an integer value of half flux quantum. Now, as I mentioned in the first point, in principle, we need that one of the junction is transparent, that has a relatively high transmission. So in the next part of the presentation, I will try to relax the point 1 by looking at different junction. And the junction we got interested in is a quantum dot junction. So at this point, we got interested about how many body interactions can affect the Josephson diode. So is it possible to increase the Josephson diode effect by including many body interactions in the system? And the simplest system that contains this kind of interaction is a single quantum dot, which is represented by this red ball coupled to 2 superconductors. The Hamiltonian is given here, where there is a Hamiltonian part of the quantum dot that is described here. So we consider a single orbital, spin degenerate orbital in the quantum dot, whose energy is controlled by this Ng that can be controlled as actually using an electrostatic gates that are illustrated in blue in the figure. We also include many body interactions as local charging energy that penalizes double occupancy in the system. So we have also the Hamiltonian part of the leads with the pairing potential delta, and also the tunneling that allows the exchange of electrons between the superconductor and the quantum dot. Now, one of the main effects of interactions is what is called the supercurrent sign reversal, or the zero pi transition, meaning that if we look at the current phase relation as a function of phase for a given without interaction, we see that it starts positive and changes sign at phase difference equal pi, while at very large interactions, it starts negative and then changes sign to positive. So there is a relative sign between weak interactions and strong interactions. And this transition may depend on other parameters like Ng or delta, but this is only just some cuts along some values. The important part is that at some point, at intermediate Coulomb repulsion and certain gate values, the current phase relation has this funny shape where it starts positive, then changes sign, and then it goes negative until pi, where it changes sign. This is what is called usually the 0 prime or the pi prime phase, because both phases coexist in the system. The interesting feature about this sign change is that actually, if we look to the supercurrent harmonics of the system, we see that there is a big first harmonic that usually dominates transport through the system that actually becomes quenched close to the zero pi transition. And at this point, there is a very high second harmonic that dominates transport through the system. And using this quantum dot, if we put the quantum dot in parallel to a conventional Josephson junction or a quantum point contact, we can actually engineer the example I was mentioning at the beginning with a sine of phi and then a sine of something that is effectively or dominated by the sine of 2 phi with some shift given by the flux. And this is what we analyze here, where there's an interferometer with a quantum dot on one side with Coulomb repulsion, coupled in parallel with a low transmitting quantum point contact, which has a sinusoidal CPR. On the left, I am representing the supercurrent as a function of the gate voltage and phase in the horizontal axis. And on the right, I am plotting the efficiency as a function again of the gate voltage of the quantum dot, tuning the level of the quantum dot as a function of the flux through the loop. As you see here, the current vanishes almost everywhere or is suppressed almost everywhere except at half filling, where the supercurrent actually becomes quite skewed. And this you see because there is a bright spot which locates to the other bright spot in yellow. And that's due to the very high transmission of the junction at half filling. And that translates to a very high efficiency that is represented on the right, which reaches values of efficiency that is of the order of 50% roughly. If we start switching on interactions, we see there is the onset of the zero pi transition that is characterized by a sign change of the supercurrent close to the pi phase. And what it does is to split the maximum of the efficiency into two peaks, which becomes more evident at large Coulomb repulsion. So when the Coulomb repulsion is very strong, we see that there is a pi phase that has completely developed. And actually, there's still some regimes where the zero pi phases coexist that are given by the cuts, where the system goes from blue to red in the range of 0 pi. So importantly, we see that the diode efficiency goes to 0 or almost vanishes in the pi regime. And the reason for that is because the current is dominated by the transport to the continuum of states that lead to an almost sinusoidal current phase relation. It also vanishes when we go deep into the zero phase, and the reason is the same, because deep into the zero phase, the current is dominated also by the continuum, which shows a sinusoidal current phase relation. And now we see there is some bright lines that appear at the coexistence between the 0 and the pi phase, and that's due to the high harmonic content of the current phase relation. Now, I have mentioned a couple of examples of supercurrent diode or Josephson diode, and now the question is, how can we optimize the diode efficiency? Well, one Josephson element that one might want to engineer is just an element where which shows some finite critical current or supercurrent in one direction, but actually has zero current in the other one. Is that even possible to engineer? Well, as we know, the energy spectrum of the system is periodic as a function of the phase, which means that the free energy, which at the end depends on the eigenenergies of the system, should be periodic as a function of the phase, with a period that is given by t. And t is usually 2 pi, but it can be also 4 pi in the case of when the junction become topological, or it can be actually a fraction, as we will see by the end of the presentation. So it doesn't matter what is the current phase relation, what is the period, but actually the Josephson current is given by the derivative of the phase as a function of the derivative of the free energy as a function of the phase, which implies that when we take the integral of the current phase relation as a function of the phase in a period, this is actually equal to 0. So that means that everything that goes into the positive direction should be compensated by a negative background or a negative or the supercurrent in the negative direction. And that means that if we want to design an element which has a zero critical current in one direction, the critical current, the positive one, should be also zero if all these conditions hold. Well, a slightly related question is, can we actually reach a regime where the diode efficiency reaches or approaches 1? And that's a situation where the supercurrent in one direction becomes much, much larger than the other one, than in the other one. Well, let me come back to the previous example with a sine of phi and a sine of 2 phi junction. And now let me make them interfere constructively on one side and then destructively in the other one. Now I can also add a third harmonic in the same way, which interferes constructively in one side and destructively in the other one. And I can add also a fourth harmonic and continue up to arbitrarily large harmonics. So this is just some screenshots or 5, 20, and 50 harmonics where I have shifted the curves for clarity. You see that the role of including more and more harmonics is to actually make this supercurrent peak in the positive direction thinner and higher, while making the background flatter a constant. So in the ideal limit, we can approach the ideal limit of eta going to 1, where in the situation where the supercurrent exhibits some kind of very sharp and infinite peak over a constant negative background, such that the integral goes to 0. But is it really possible to engineer this kind of Josephson element, or is it possible to actually optimize the Josephson diode to arbitrarily large efficiencies? Well, to test this idea, or to try to answer this idea, what we did is to design an element composed by n quantum point contacts, in this case for simplicity, which are concatenated in parallel. And we consider they are single channel quantum point contacts whose parameters can be tuned. So the transmission can be tuned using, for example, electrostatic gates, and the flux through the loops might be tunable using micromagnets. And of course, these kind of devices might be very challenging to control experimentally when there are many, many loops. But I think it's still a reasonable theory questions to try to understand what is the limit of this kind of model. So this is the result we got using a maximization Monte Carlo algorithm. As you see, to get this curve, what we did is to optimize all the transmission and all the fluxes independently to get the highest efficiency possible. So as you see, for 2 quantum point contacts, the maximal efficiency approaches 0.4, while for 3 of them, we can reach something that is of the order of 55%, which means that the critical current in the positive direction is about 4 times larger than in the negative one. And the curves continue growing when we continue adding more and more junctions to the system. We have developed an analytical bound for the maximal diode efficiency using n elements that are not diode themselves, and this is the expression we have developed. And I can come back later to I can come back to it later if you are interested. Now we can have a look to the current phase relation to the different junctions. So for 2, 3, 4, and 8 junctions. And we see that the effect of adding more and more junctions is to make the supercurrent peak in one direction actually narrower and a bit higher. But one of the main effects is to make the background, so the negative background, a bit higher. So this is the way the supercurrent, this is the way that interference can help at increasing the diode efficiency in this kind of devices. So I'm going to devote the last part of, or almost the last part of my presentation to how to detect the Josephson diode effect. So in previous experiments, people used DC current measurements to actually measure the diode efficiency and to determine whether there is a supercurrent diode or not. Here we are interested to go a step beyond that and use the AC driving current to actually see the signatures of the Josephson diode So to look at the Shapiro steps. Just as a reminder of the RSJ model, where we put a DC and AC current bias to the system, and now we consider that the Josephson element that is on this part is a quantum point contact interferometer, like the one I've shown at the very beginning, which is coupled in parallel to a resistor. Now, the differential equation for the phase as a function of the time depends on the DC and AC current bias. And actually, the time derivative of the phase is related to bias voltage drop at the two terminals of the junction. Now, if there is no diode effect and there is no AC driving, this is the kind of curve we see where when we start increasing the DC current in the vertical axis, at some point the system starts to become resistive. And that's the place where we can measure actually the critical current in the positive and the negative direction. So finding an asymmetry between the positive and the negative direction might be a signature of the Josephson diode effect, although one needs to be careful about the switching and retrapping current, which can lead to some artificial asymmetry, but I'm not going to enter into that details. Now, in the AC driving case, what we see is that instead of having one jump and then having a more or less constant resistance, so it has several jumps to multiple values of integer values of the driving frequency for the bias voltage. So the question is, what is the diode? How the diode effect influences this picture? And this is what we represent here. When we look at the diode effect, one of the main effects is that actually the step in the negative direction and in the positive direction become asymmetric. And that's due to the difference in the critical current in both directions. This is better seen in the right part where we plot these two heights. And as you see, they have different height, but there is also some offset between the curves, which might be a signature of the diode effect. Now, the second way of seeing the same picture is by looking at the differential resistance map, where we put the DC current bias in the vertical axis and the AC current bias in the horizontal one. If there is no diode effect, what we see is a symmetric picture with respect to the IDC current, which means that actually the picture, so there is no diode effect, because actually the transition between the superconducting to the resistive regime is symmetric in the positive and the negative direction. Now the situation becomes a bit qualitatively different when we add an element that has a significant diode effect. And as you see now, when we sit down at 0 AC driving current, the transition to the resistive regime becomes different in the positive and in the negative direction, and that's due to the response of the diode effect. But it also leads to some Shapiro fan pattern that is actually asymmetric, and some Shapiro steps that actually cross not at 0 DC current, but at finite DC current. And this is a signature of the Josephson diode effect. Well, I'm going to spend the last couple of slides in my presentation trying to go a bit beyond of the Josephson diode effect and giving, well, one potential use of the diode effect. So up to now, I have looked to interferometers with several kind of junctions. One example was two quantum point contacts set into in between two superconductors, which is now represented as gray. Actually, if we these quantum point contacts have a single channel and they are tuned to a situation where there is where the transmission is equal, and we thread a half flux quantum through the system, we can make an interference effect where the transfer of Cooper pairs between the two superconductors is quenched, and then transport is dominated by processes where two Cooper pairs are transferred between the two superconductors. And that has been proposed in the last years as a way to develop protected qubits for quantum information storage and processing. And this is one effective Hamiltonian where we have the charging energy similar to the transmon qubit, but then we have a Josephson junction that now is has double periodicity in the argument. And the idea is to store information not on the fermionic degree of freedom, but on the on the parity of the Cooper period in the two islands. Let me mention very briefly, that there were a number of works in this direction, starting from early experimental realization and then coupling several of these elements and entangling them with transmons. But in this presentation, I'm more interested in how to tune the system into the protected regime. So in the regime where the two transmissions are equal and the flux is actually half flux quantum. So this is the regime where one would like to operate this kind of qubit. So when we are slightly away from the protected regime, we see that there is the conventional integer Shapiro steps, but there are some fractional Shapiro steps appearing as these small kinks here that are denoted in red. And this is a signature of the transference between of two Cooper pairs between the two superconductors. When we tune the system to the protected regime, actually these Shapiro steps double and they become equally in height, which is a signature of the system to be tuned to the protected regime. Let me say that the quantum point contacts don't need to be tuned to such a high transmission to reach this regime, but the only condition is that they are equal. However, the effects and the protection become better the higher the transmission, of course. Now, we can also see that in the differential resistance, where we see that the unprotected regime has some Shapiro steps that actually can split depending on how far we are from the protected regime. So this is close to the protected regime. And in the protected regime, we see that these Shapiro steps has actually split and they become evenly spaced, as you see in the right picture. Now, how does it relate to the diode effect? Well, actually, we would like to set up the system to this yellow star where the two transmissions are equal and the flux is actually half flux quantum through the loop. If we sit down at this point, there is actually the diode efficiency or the diode effect is actually negligible. But once we move away from this point in almost any direction, we see there is a very strong diode effect. So this diode effect can be actually a way to tune this kind of qubits, or to help to identify the protected regime in this kind of qubits. And actually, we can also go to more exotic regimes with junctions where actually transport is dominated by the 6 electrons between the transfer of between 6 electrons between the superconductor, and expression for the transmission and the phases of these junctions is given in the appendix of our work and also given here. Now, let me conclude by saying some remarks about our work. So we have proposed Josephson diode based in supercurrent interferometers. We have analyzed the role of interactions, determining that actually the diode effect can be enhanced by the transition between the 0 and the pi phases in quantum dots. We have found or developed a systematic way of optimizing the diode efficiency. And also, we have proposed a way to detect the diode effect based on not only on DC current bias, but also on AC current bias. And with that, let me thank my collaborators, Martin Leijnse, Constantin Schrade, and thank you all for your attention. Yeah, of course, I'm happy to answer any question. So please feel free to unmute yourself and ask direct questions.
Hi, I have a question. Can you hear me?
Yes.
So you mentioned that you need quantum point contacts in this interferometer. So is it so in quantum point contacts, we usually think of like very few conductance modes doing the transport. So is there like an upper limit on what's the number of conductance modes should be for this thing to work?
No, no. The only thing we need is higher harmonics. It means that there could be a million channels, but it's enough if only one of them or few of them are very high transmitting. The important thing is that the current phase relation should be skewed. Should have some high harmonic contact. So if you take the Fourier transform of the current phase relation, there should be some high harmonic contribution.
Thank you.
Hello, Rubén. So I have a question regarding inductive effect, because when you have a loop and you pass a flux, you also have inductance. So you will have to calculate this current cell consistently. So how robust are your, your results when you take into account inductive effect in these loops?
Well, we haven't taken that effect into account, but okay, this is the efficiency of the diode as a function of the flux and as a function of the transmission. And I would say that the norm is that actually the diode effect is everywhere except for some fine-tuned situations. That is, the equal transmission situation and the flux. So my expectation is that the superconducting Josephson diode effect will still persist if we include this effect.
Right, but would this have all these, symmetries or these properties that you have, or so how, the large values that you have will be still there if you have inductive effects? So.
Yeah, that's a very good question. I don't have a good answer to that. I don't know if the inductive effect will boost the diode effect or will suppress it, but I think it will be still present. And I think that's a question. That's a very interesting question that should be investigated for sure.
Thank you.
Thank you.
Also have a small question. Thank you for the nice talk. Could you go to your conclusion slide? There's this the figure of the Shapiro steps, and there are some half integer Shapiro steps at low powers, right? In this case, positive bias. And so in what extent do these half integer Shapiro steps actually tell you that you have a diode effect, or to what extent is it that simply you have different harmonics in the current phase relationship and therefore also half integer steps?
Yes, so this small, I guess you're referring to this small split in that of the Shapiro steps here.
Yes.
They don't, I mean, this small splitting is only related to high harmonics. They don't say anything about the diode effect. I mean, they are present, for example, well, for example, in this picture in panel A, there is a very small diode effect that is almost vanishing because you see there is no asymmetry between the positive and the negative one. So there's a tiny, tiny, tiny diode effect, but still there is some splitting. And actually, they completely split in the right-hand side where there is absolutely no diode effect. So the splitting of the Shapiro steps only tells something about the higher harmonics between the two superconductors. The asymmetry is the one that tells you about the about the diode effect.
I see. All right. And one more question. That is, why do they disappear actually, these half integer steps at higher powers?
That's a very good question. I don't have a very good answer to that, but it seems they actually split and recombine at some point. I don't have a good explanation, unfortunately.
Okay, no, that's fine. Thank you very much.
Thank you.
This may not be, maybe I just don't have the required background to fully understand, but I'm not sure why you get the, well, earlier from the presentation, why you get the different periods in the, well, for example, just there, why, how you can get the, well, the 2 phi period there. Is that just a feature of the quantum dots?
Yeah, this is a feature of the quantum dot. that actually there is, I mean, you need to interpolate between the black curve and the blue curve, and the way that nature interpolates between them is by giving some kind of sawtooth behavior.
Right.
And then when you Fourier transform that, it happens that there is a second harmonic that is very high, and then there is a first harmonic that actually suppresses, because the first harmonic has to go from positive to negative.
All right. Thank you very much.
Thank you.
If I may, I have a comment on one of the previous questions about the inductance. If one takes the good old book of Baroun and Paterno, one sees that in general, a completely conventional squid with sinusoidal current phase relation. So if the two arms are asymmetric, let's say with different inductance, your as a function of the flux, the figure will be a bit tilted, and actually you have a diode effect in the general case. So are these effects in a way kept into account? If I understood correctly, not yet. But my guess would be that this might contribute. So because ultimately they produce a let's say conventional diode effect in a completely sinusoidal current phase relation. So I think it might play a role.
Yeah, thank you for the nice comment. Would you mind writing the book in the chat?
Yes, is a physics and application of the Josephson effect. Let me write to all. Sorry, not physics and application of the Josephson effects for experimentalists. This is the Bible of it's an old book of the late 70s. And so it's quite outdated. It's just an example to say that if one goes into chapter 12 is the squid, one sees a graph, as the one I said. And there are quite examples of that. Just want to say that or when one has a out of plane field and one can play with orbital effect, having a diode effect is more the rule than the exception. So one can also have, for instance, a inhomogeneous Josephson junction, rectangular, inhomogeneous plus out of plane field. The Fraunhofer pattern will be tilted, and in general, one has effect, which maybe one can use it in a new fashion to observe to get something new. I'm not saying that everything is just old. I mean, it's but my comment is that if this can generate a diode on its own, might have or might not have a role in what you are studying, which is different. Instead, is the use of the higher harmonics to engineer this in a different way, even without different inductance for the two junctions.
Yeah, thank you. I think this is a very nice comment and very relevant, saying that, well, maybe we haven't discovered the diode in the last few years, but we have probably named it in the last few years. And I think it's a very interesting. I was not aware of those examples, so I will check them. Thank you.
You can check chapter 12. There is there are other examples. What I might say is that I think what became, at least in my view, relevant in the last years is the fact that one can play with these things with the spin instead of orbits. In fact, it's most of the case we have Rashba, magnetization, and so on. But of course, also attract the interest of how to play with these things in different ways. So I'm absolutely not saying that with orbital effect one cannot do anything interesting. So it's absolutely not that. I just want my comment was that it might play a role. Of course, that must be summed or subtracted. I don't know. This I cannot tell.
Yeah. Thank you.
You're welcome.